Hey everyone, and welcome to this explainer brought to you by Forge College. You made it! You survived the last lesson on synthesis and operational playbooks, and now we are officially kicking off the capstone module of the Ether and Advanced State Management course. You've mastered all these isolated patterns, right? Well, today's the day we knit them all together into one comprehensive master plan.
Here's the blueprint for today's explainer. We'll kick things off with the warehouse metaphor, then tackle the custody question, walk through a concrete 6-step workflow, apply that to building a multi-escrow, and finally lock it all down with operational safety.
All right, let's jump straight into Section 1, the warehouse metaphor, structuring your smart contract. Before writing a single line of reduction code, you really need a solid mental model. So, think of your smart contract design like drafting architectural blueprints for a massive, bustling warehouse. Your Solidity storage slots, those are your labeled shelves. Your structs are the crates that fit perfectly onto those shelves. And Ether is your highly valuable, perfectly fungible, transferable inventory. Keeping this physical space rigorously organized is absolutely crucial. It literally translates to saving a fortune in gas and operational overhead.
And just like in the physical world, we have massive workplace safety hazards here, basically Web3 OSHA violations. Good bookkeeping means your shelves are properly labeled and updated instantly. Poor bookkeeping, that's like leaving the loading dock doors wide open. While your contract is slowly updating its ledger with a pencil, auxiliary actors like malicious re-entrance hackers sneak right in and just walk away with your Ether inventory because the system didn't realize it was already gone. Yeah, no thanks, we definitely don't want that.
Which brings us right to Section 2, the custody question, holding versus routing inventory. This is, without a doubt, the most critical architectural decision you have to make before laying down any storage code. Does our warehouse actually hold inventory long-term, or just route it? You have to ask yourself, is your contract acting as an escrow vault guarding assets for months, or is it just a transient shipping router blinking funds through in a split second? Your answer fundamentally changes the entire shape of your state. Here are the trade-offs. Long-term custody means you have to pay the persistence costs. It requires explicit mapping structures and explicit reclamation paths because somebody eventually has to get that inventory back. Routing, on the other hand, means you manage a lot less state, which is great, but you have a much higher surface area for transfer failures. If a transfer fails mid-route, you need strict atomic settlement and poll semantics to revert the whole thing safely.
Okay, moving on to Section 3, the 6-step workflow from requirements to architecture.
This is the repeatable sequence that turns your abstract requirements into concrete Solidity code. Step 1. Invariants. What are your absolute truths? Step 2. Entities and access. Who interacts with what? Step 3. Data shapes. Are we using structs or mappings? Step 4. Storage layout. Packing everything tight for gas optimization. Step 5. Custody and flow. Modeling exactly how the Ether moves. And finally, Step 6, events and reversions, mapping exactly where and how things should fail.
This workflow acts as a quick architectural cheat sheet, where real-world components map perfectly to gas-optimized Solidity constructs. Need a per-user balance? Map an address to a UN256 for efficient pull withdrawals. Multi-escrow records? Use a nested mapping with per-owner counters. Got bulky dispute metadata? Definitely keep that off-chain, using something like an IPFS hash. And for routing-only flows, keep those functions stateless, but be super careful with your atomicity.
Let's see this in action. Section 4, building the multi-escrow, applying the workflow. Applying our shiny new workflow to an actual capstone project, here are the exact data shapes we need for our escrow struct entity. We need addresses for the maker and the taker, a UN256 for the exact Ether amount, 2 UN64s to track the creation and release timestamps, and a simple Boolean flag to check if it's disputed. Now pay attention to the magic number here, 1. By cleverly picking our data types, specifically packing those two 64-bit timestamps and the 8-bit Boolean together, we can fit all of them into exactly one single storage slot. This is a massive, massive optimization that saves a fortune in gas every single time that escrow is read or written. So how do we find these specific crates in our massive warehouse? We use nested mappings. We map an address to another mapping of an integer to the escrow struct. Combined with a per-owner nonce, which is basically just a counter for each user's escrows, this acts as a highly efficient indexing system. It completely avoids the dreaded unbounded array iteration, which, as we know, is a gas-guzzling danger and a total anti-pattern in Solidity.
All right, home stretch, Section 5, operational safety, checks, effects, and pulls.
You've built this beautiful warehouse, but how do we lock it down against malicious actors? The safe route is the checks, effects, interactions pattern. You update your ledger first, say, setting the owed amount to 0, you emit your event, and only then do you transfer the ether. The reentrancy hazard is doing it backwards, transferring the ether first and then trying to update your books while the attacker is already looping back inside for more.
If you remember absolutely nothing else from this explainer, I want you to tattoo this on your brain. Move state first, transfer later. That is your golden rule. It is the ultimate bulletproof defense against reentrancy in your capstone and honestly, your entire Web3 career.
And that perfectly sets up another critical safety mechanism, the pullover push pattern. When a complex state transition happens, please don't force outward transfers. Pushing ether to arbitrary addresses is incredibly risky. They might reject it, or they might just run out of gas, which causes your entire transaction to revert. Instead, record the owed amounts in a pending withdrawals mapping. Let the users pay the gas to claim their own funds.
Before we wrap up, let's just rapid fire a few final architectural best practices. Always store bulky, dynamic dispute evidence off-chain on IPFS. Keep your on-chain event payloads small and punchy. Lock down your functions with explicit modifiers like only maker or taker. And always have a fallback plan for failed transfers. Remember, efficiency and security are not competing goals here. They go completely hand in hand.
So, are your warehouse blueprints ready to become concrete storage patterns in the next lesson? I think they are. Thank you so much for joining me for this explainer by Forge College. Be sure to head over to forge.college to master more Web3 topics and continue your journey into advanced state management. Until next time, ask yourself, if your smart contract warehouse was audited by a hostile hacker tomorrow, would your shelves pass inspection? Keep building, stay safe, and I'll see you in the next one.